Good morning, everybody. Today, actually, I'm going to start the electronics part. Electron is basically semiconductor part. In NetGate exam, only simple question asked based on the semiconductor part, and I strongly advise you to study Donald Newman Introduction to Semiconductor Physics. If you study this book, and only some specific portion you have to study, and numeric and NetGate question comes from semiconductor and transport phenomenon and Hall effect. This is the three important parameter, important section you have to study. Okay, and basic thing you have to understand. First of all, I'm going to focus on the basic things. After that, I will start. And what are the things you have to remember? What are the things you no need to focus? That part I am going to discuss here. Okay. So semiconductor, I am starting from basics so that you can understand. Semiconductor. What is semiconductor? Okay, semiconductor is a one class of material that has low concentration of electron. Normally in metal concentration 10 to the power 828 cubic meter. Okay, in metal. And insulator is a electron concentration around 7 cubic meter. It is fall in this range. But in semiconductor, the concentration of electron falls in between these two. That is why it is known as nomenclature as semiconducting material. Okay, but another special characteristic is that in metal, what happens if we increase the temperature or if we increase the thermal energy or voltage, whatever it is, if we apply electric field, then what happens? Metal, the mean collisions between free electron will gradually increases. As a result, resistivity is increases. Okay, but in semiconductor, that thing is not happen in semiconductor. So in semiconductor, when you increase the temperature, the number of carrier from valency band to conduction band gradually increases. So number of available carrier increases. That is why it is always called as a negative coefficient of material. Negative coefficient of temperature. That means when you increase temperature, the concentration in electron, the semiconductor gradually increases. Okay, that is the basic difference. Okay, now first of all, what are the semiconducting material? First of all, there is a two type of semiconductor. One is a direct band gap semiconductor, another is an indirect band gap semiconductor. Okay, and before understanding the semiconductor, direct band gap semiconductor, indirect band gap semiconductor, we have to understand what are the semiconducting material. First of all, group 4 element. Group 4 element, if you focus carbon 6, 2, 4, silicon 14, 2, 8, 4, germanium 32, 2, 8, 18, 4, and SN, PP. This is the group 4 element of periodic table. So it is group 4 element. Why it is called? You see the outer valence shell electron composed of 4 electrons. Okay, this is also 4. This is also 4. We know, we have already studied in chemistry. The outermost shell is maximum 8 electron can be accommodated. Outermost shell. Suppose this is K cell, this is L cell, this is M cell, like that. 2 electron here, 8 electron, and 18 electron is like that. So in case of semiconductor, in outer valence shell, it's composed of only 4 electrons. Okay, 4 electrons. But according to principle that outer valence electron, it necessary how many electron? 4 additional electron is necessary to complete this cell. Okay, it should be 8. So 4 electron is necessary. So from where this electron will get? So this electron, 4 electron, the outer valence shell will pair with another silicon or another germanium, so that the 4 electron will combine and sharing the covalent bond will form. Okay, but you see, you know this cell, suppose first S2, twice S2, twice P6, this type of cell structure. So we have already studied this type of. outer cell necessary 8 electron, but when it is suppose 2, 8, 3, this is 3, then it is less than half fill. Half fill is 4 electron, this maximum full fill is 8 electron. Half fill means 3, less than half fill hole, that means it can give the electron to other. So if it is more equal or more than half fill, suppose it is more than half fill, suppose outer valency electron 5, then it will take 3 extra electron. Okay, when it is 4, then it will sharing will take place with another similar atom, so that bone formation is completed. Bone formation means it will complete 8 electron. So that means semiconductor is always from a covalent bond. Remember, this question comes. Always from a covalent bond, and where it is group 4 element, it is outer valency electron. Valency cell composed of only 4 electrons: silicon, germanium, Pb, Sn, whatever it is, group 4 electron. Okay, these 4 electrons will combine with 4 electrons. Suppose if we talk about silicon, germanium 32, silicon is 14. Silicon 14 means 2, 8, 14 means 2, 8, 4. So a crystal is what? Semiconducting crystal means composed of large number of silicon atoms. Okay, suppose this is a semiconductor, silicon semiconductor. Then a large number of silicon atom is there. So every atoms would it will form a covalent bond with nearby silicon atom. So for it is happen. Suppose silicon 2 atom, if I consider, this is 4 electron. 4 electron I will replace like this. This is 4 electron, and 2, 8, 8, 4 electron. So it will form a covalent bond, and then it will become as a 8. Okay, this is how covalent bond formed in semiconductor. So if we see the covalent bond, silicon, suppose germanium is also 32. Germanium 32 means 2, 8. Germanium cell structure 2, 8, 18, 4, 32. 32 is there. So it will, suppose this is germanium. This is also germanium. This is also germanium. This is also. Then what happened? This is form a covalent bond. Covalent bond. This is germanium. This is 4. This is form another. This is 4. This is 4. This, see, germanium, this is outer valency electron, 4 electron. These 4 electrons share with similar germanium atom. So finally this is the covalent bond. Covalent bond is formed. So and finally it becomes stable. Okay. So that means group semiconductor always form a covalent bond. Now, what is it based on band gap? Band gap we have already studied in conic penny model. I am not going to detail the conic penny model because we are going to study again in condensed matter physics. Okay, conic penny model, the band structure. Ideally, so far we have studied. This is a valency band. This is a valency band, and this is conduction band. This is supposed conduction band. This is ideal that we have studied. Okay, practical band gap is from conic penny model. We find this. This is conduction band. This is valency band. Okay, this is band gap. This is a band gap. Band gap is represented by this. This is a band gap. Okay. Now you may ask question: what is a valency band and what is a conduction band? Conduction band, valency band is a band formed by closed cell electron. Closed cell means that band formed by electron which is very close to the nucleus. For example, if we consider the nucleus, this is nucleus, this is K cell, this is M cell. This outermost cell, this is K cell, this is M cell, this is M cell. Outermost electron almost considered a free electron, and this electron always contribute to the electrical properties of material. Electrical property means it will show conductivity, it will show any other epsilon property, permeability. So electrical property, and the band formed by closed shell to the nucleus is called valency band, and band formed by outermost shell electron, which is very less shielding effect. Shielding effect means the outermost shell electron has a less attractive force with the nucleus. So that electron you can consider as a free electron. Okay, band formed by outermost shell electron is called conduction band, and band formed by valency close to the nucleus is called valency band. Okay. So this is ideal figure. We have already studied in the book SSDSC, whatever it is. Actually band structure is not look like that. It is band structure, is practical band structure is look like that. Okay. This is a band gap. Band gap means this is the forbidden region that we have already studied in conic penning model. In this region there is no possibility of finding any electron. Okay, expanded source. This only band at low temperature. What happens? All electron will fall in the valency band, and conduction band there is no electron, and at low temperature semiconductor at low temperature means at T equal to 0 Kelvin semiconductor behave as an insulator because of lack of electron in conduction band. Okay. Now this is a band structure. Now next question, what is a direct band gap semiconductor? What is an indirect band gap semiconductor? Direct band gap semiconductor, direct band gap semiconductor, and indirect band gap. Indirect band gap. Direct band gap semiconductor is C. This is a conduction band, direct band gap. This is a valence band. This is a actually it is draw in K space. This is energy curve. Okay. And this direct band gap semiconductor, electron, this is a band gap, this is a direct band gap, this is indirect band gap. This is conduction band, this is a valency band, and you can draw like this. We have already studied in conic penning model. This is along A, this is energy. Okay, this is a valency band, this is conduction band. But valency band, this is a conduction band. So in this will be band. Okay. So direct band gap semiconductor, there is a two type of semiconductor. One is called direct band gap, one is called indirect band gap. Direct band gap semiconductor is our direct band gap semiconductor are group 3 and group 5 element. So you have some basic idea about periodic table. Group 3 element are what is a group 3 element? Indium, beryllium, this other. This direct band gap semiconductor, compound semiconductor. Suppose indium phosphate, gallium arsenide, AS. This type of semiconductor formed by group 3. This is indium group 3, phosphorus, gallium arsenide group 3 and group 5 element. It's always called direct band gap. What happens direct band gap? Direct band gap semiconductor, the electron VB, electron from valency band directly move to the conduction band. That is a direct band gap semiconductor. And indirect band gap semiconductor, what happens? The valency band electron will move to the tap center. This is called tap center. It will not, suppose I am sending you, suppose I am going to Guwahati from Tezpur via Nagaon. Okay, somebody is coming from going from Guwahati or Tezpur to Guwahati directly. Okay, that is happening here. But here what happened? This electron from valency band move to the tap center and then move to the conduction band. Ultimately what happened? This is in case of indirect band gap. Okay, ultimately what happened? The response of this semiconductor is slow as compared to direct band gap semiconductor. Suppose you consider remote. Okay, if you press the switch, particular switch 530, then what happened? We as according to our requirement, it should, the TV channel should change quickly as possible. But here indirect band gap semiconductor, once you press the switch, after few seconds, few microsecond or few nanosecond, whatever is a few minutes maybe, so it channel will change. We don't need this type of response device. Okay, we need a direct band gap semiconductor so that valency band moves to conduction band, and it will, after that it will at equilibrium position, it will electron will fall from the conduction band to ground valency band, and it will emit the radiation. Radiation means its response. Similarly, this is indirect band gap. Indirect band gap, which are the indirect band gap element? Group 4 element. Group 4 element is semiconductor, suppose silicon, germanium. This single element is semiconductor. Silicon, germanium, these are the indirect band gap semiconductor. Okay? But we, according to our requirement, we need the direct band gap semiconductor, which are the compound semiconductor. Indium phosphate, gallium arsenide. But one or two compound semiconductor also fall in the indirect band gap semiconductor. I am going to give you the detail. Okay, this is the basic idea about semiconductor. Okay, this is a theoretical and graphical explanation of semiconductor and classification of semiconductor. Okay, and now come to the hole and electron concept. Hole and electron concept. What is a hole? What is electron? Hole and electron. Okay, whole concept in semiconductor is a totally hypothetical concept. Okay, suppose this is my room. This is my room. This is two chair, and two person is sitting this side. This is person. This is my room. This is person P1, person P2. Okay, and these two chair is vacant. Back. And another diagram. Suppose this is a P1, P2. Suppose this person P1 and P2 is electron. P1, P2 is electron. Okay. Okay. Now again focus on this diagram. In the first diagram, there is a suppose total number 4 chair. This is my room. Suppose. Okay. Two person is sitting one side. Okay. Suppose that side, two person is sitting there, two chair is vacant this side. Okay, if two person move from that side to this side, to this person moving this side. This person initially sitting here, and after few seconds or few minutes, it will move to this chair. Then it look like this vacant chair move from this direction and fifth chair move this direction. Okay, so practically the whole is never moved. Whole is, it look like that this vacant chair move this direction, this filled chair means two person sitting in that chair is move this direction. So electron hole concept is similar. Okay, one electron move from that side to this side and vacancy become there, and here vacancy is fill up. It look like the electron moving this direction and hole moving this direction. Okay, clear? I hope you understand. But one thing is, remember, that is why in semiconductor, if electron moving this direction, hole will moving this direction. Hole will moving this direction. But whenever we encounter a transport phenomenon, for example, current, when we are going to calculate the total current in semiconductor, we will count the total current is the current due to the electron as well as hole. But this current, if I take this is a suppose silicon semiconductor. Okay, if I take a wire, this is a wire, copper wire. This is after giving some voltage or current, whatever. I am not going to draw the whole diagram. Okay, after giving suppose voltage, the electron moving this direction, hole moving this direction. Okay, hole moving this direction. I am getting the current this direction. Okay. Okay. Then outside the semiconductor, there is no concept of hole current. Outside semiconductor, hole current exists inside the semiconductor only. The outside semiconductor, there is no contribution of current due to hole. Remember, this is a very basic question. And direction of current is always taken as the direction of opposite movement of electron. Well, suppose I am giving an example. If you want to remember, suppose if two person P1 and P2 running, suppose these two person is running this direction, along suppose x direction. Okay, then what happen? If this person look at this person, or if this person look at this person, they cannot see the relative motion. Okay, only whether you are running or not, if you want to ensure somebody must be opposite side. So when you cross we come to know that this person is moving, I am also moving. So similar concept is here. That conventionally the direction of current is always taken against the direction of electron. Always electron moving this direction, current will be this direction. And whole current does not exist outside the semiconductor. Okay. I will tell you detail and I will tell you so whole diagram when I teach you this diode. Okay. I will tell you basic semiconductor part. Basic semiconductor part you have to study construction of semiconductor, phenomenon of semiconductor, and then transport phenomenon of semiconductor and Hall effect. After that we will move to the diode, and after that we will move to we parallelly start two things. Semiconductor I start today, and after that I will start transistor, then I will teach you diode. Okay, and then I will move to the op-amp. Most of the question comes semiconductor, op-amp, and one or two question from transistor. Transistor basically field effect transistor. Okay, and circuit analysis. Circuit analysis is very easy, and I will teach you how you can do the circuit analysis. This is the whole concept. Okay, now we are going to calculate. Now we are going to calculate the concentration of electron. We have already know, we come to know. I am not going to give you details all the semiconductor structures, how it is formed. I will tell you detail. First of all, I will talking about intrinsic semiconductor. Okay, what is a intrinsic semiconductor? What is a non-intrinsic semiconductor? What I am going to tell you. Extrinsic semiconductor, intrinsic semiconductor. What do you mean by intrinsic semiconductor? Okay, normally student intrinsic semiconductor. Intrinsic semiconductor, what do you mean by intrinsic semiconductor? Intrinsic don't give this definition that the semiconductor which has the electron concentration equal to hole concentration. This is not correct. Okay. The semiconductor which is purified in such a way that the impurity inside the semiconductor is minimum, so that number of electron equal to number of hole. Okay, that type of semiconductor is known as the intrinsic semiconductor. Suppose inside this room, this is my room, total 4 chair is there. 1, 2, 3, 4. 4 chair. Two person is sitting. Okay, and this is 2 hole. Hole means 2 vacant chair, and electron means 2 filled chair. Okay. Suppose I consider this is equal to n equal to p. Okay, number of hole is equal to number of electron. But you have to ensure there must not be any person inside this room. There may be some person somewhere hiding inside the room. If somebody is there, somebody inside it, suppose inside your bed or below your bed is sitting, idly keeping him inside your bed, then he may occupy this chair. Then number of hole equal to number of, it will not become equal. So intrinsic semiconductor is semiconductor which is purified in such a way that the number of hole equal to number of electron. Okay, this is the main definition. Okay, now we are going to calculate the concentration of electron in concentration of hole. Before going to that, I have to discuss what is the concentration of electron. Concentration of electron first in conduction band and hole in VV, valence. How to calculate? So in this case you have to understand what is the density function. I have told you the statistics. Okay, statistical mechanics we have already given you the general definition. Density of state is, I am not going to derive all this formula. I will give you the general formula. Density of state, this is a general formula, E d by s minus 1. Okay, this is the formula. E G is density of state. It is calculated like that. Calculated from here. G into 4 by 3 pi p cube is, this is in statistics. Then g equal to d sigma by d equal to how much? If you do this calculation, 4 pi v h cube y same c by 2 e half. This is the density of state in case of 3D. Okay. I'm not going to give you detail. I have already given you the density of state. This is the general formula you have to remember. Okay. Now I am going to consider the electron. Okay. Electron, what is the dispersal? Electron is a fermion. And classical, I am considering a relativistic concept is not applied. So normally, what is the energy of the electron is equal to p square by twice m. P equal to h cos k. We have already studied in condensed matter physics, h cos k square twice m. So E means proportional to k square. This is called S value. Okay. This G general formula equal to a constant I will put it here, e to the power d means d is a dimension. Okay, I am considering a crystal in 3-dimensional case. I will put it t by 2 minus 1, so it will be a e half. This is the density of state in 3 dimension. Okay, for only for electron having this special relation, this one. But this density of state will be different for phonon and all boson particles. Okay. Or you can, I am giving another general formula from where you can calculate the density of state equal to Lx, Ly, Lz and equal to 2 pi d-dimensional space. Okay. This is general formula for d-dimensional space. Integration d to the power d k. If you do the calculation, you can find out the full density of state. Okay, this equal to 4 pi v h cube. Okay, y same 3 by 2 e half. This constant means this one e half. This is the density of state. And if you want to calculate, you can, this is whatever I have already in previous example I have given you, that is in statistical, from statistical. You can calculate from here also. In 3 dimensional, you see how can I calculate. 3 dimensional, this is L cube means V. Okay, Lx, Ly, Lz, in 3 dimensional it will be V. 2 pi to the power T. See, this is in moment, K space. Now I have to convert in momentum space, then it will be easy. I will remove this part. So I hope you understand. So it will be, see, P equal to h cos k. So dp equal to how much? H cos dk. Then dk equal to, it will 1 by hd integration d to the power dk. Sorry, p. Okay. This equal to v twice pi cube h cross. H cross means h cube by 8 pi cube. This part cancel into a d to the power 3p. Okay, so it will be how much? D by h cube integration d cube p. Okay, so I am taking it here. I have already given this general formula in statistical calculation. I am giving you again so that you understand. So I am getting v by h cube d cube p. D cube p means d cube p. What is d cube p? In statistics, I have told you omega total volume in microspace. Total volume, what is the number of microspace? It is what? V Cartesian into Vp. This is equal to V. This is equal to 4 by 3 pi p cube. This is volume of momentum space. Okay, total volume in statistical space, this means momentum space. This is Cartesian volume, this is momentum volume. Momentum is a sphere that we will going to study again, Fermi sphere in condensed matter physics. So this will equal to V by h cube. This is 4 by 3 pi p cube. Okay, see what we are getting in statistics. In statistics we consider omega, number of microstate E is equal to how much? total volume V into 4 by 3 momentum volume, momentum sphere volume is h cube. Okay, see, then number of energy is equal to density of state equal to d sigma E d. Now if I replace P means what? P square by twice m equal to E for electron. Okay, don't write this expression for photon or phonon. This is only for electron, or only for electron or particle that followed up dispersion relation. This one, dispersion relation is proportional to K2. This I'm telling again, this density of state function is valid only for particle having dispersion relation is proportional K square. Okay, density of state depend on dimension as well as dispersion relation. This equal to what we are getting? If I replace this one, E equal to 4 pi V H cube and twice m half E half. Is it okay? Density of state. And then G equal to GD equal to 4 pi V H cube twice pi or twice m 3 by 2 E half dE. Is it okay? Now you can calculate from here also. Density of state, if you calculate from here, you will get the same formula: 4 pi V H cube twice m 3 by 2 E half dE. Same, you can calculate from here. Density of state, you can calculate from here. Okay. But this is only for 3D. Suppose some calculation in books you will get the any density of function only for electron, only for photon. But they never mention the dispersion relation and general formula. You focus on the general formula. Suppose. And second thing is that in books they have do all the calculation for 3-dimensional case, but they never consider for D-dimensional space. D-dimensional space means D means 2-dimensional, D means 1-dimensional. How to calculate density of state in 1 dimension? I am giving you example again. This is the general formula: Lx, Ly, Lz. 2 pi d. This is a D-dimensional space. Integration d to the power dk. Okay. Then if we transform this one, putting this value h cos k, then it will transform to twice. Lx, Ly, Lz. 2 pi d 1 by h cross d integration d dt t. This is the general formula in terms of momentum. This is in terms of k space. K space is also known as the momentum space, but it is only in terms of momentum. It is in terms of wave vector. Okay. Suppose in 2-dimensional case, how to calculate density of state? So 2-dimensional case, this G d equal to then you have to put either one Lx, Ly. Okay. Then twice pi into 2. Then 1 by h cos 2. Okay. I am removing this part. H cos 2 integration d square t. Okay. Now you have to focus this L square. This is I am putting a Lx equal to Ly. Okay. Simplify that one. This is twice pi square. This is a square by 4 pi square. Okay. dpx dpy. Clear? Clear. Then it will be cancel this part. L square by h cos square. This is p square. Is it okay? P and p. Total p square. Okay. What you are getting? Density of state in 2D case. G sigma E equal to L square. L square means area. You can put. Okay. Then h cos square p square. P square means p square by twice m equal to E. P square equal to a by h cos square. Clear? Not h cos, h square. And p means what? P square means twice m E. Okay. Clear? In case of 2D. Then G equal to how much? The differentiation of this part. D sigma d equal to a by h cross h square twice m. Constant. So density of state d equal to A by A square twice M mass and d. That means what? Density of state G equal to constant. Suppose C, I am putting this is all constant, C constant. Is it okay? You can calculate this way. Then from general formula you can see. The general formula I have given, this is, that's why I am giving the general formula, E d by S minus 1. So in this case, the S integer value of dispersion relation is 2. So it will be proportional E d by 2 minus 1. Okay, proportional to E how much? This is 2-dimensional case, 2 by 2 minus 1 equal to constant. Is it match? See, match. So my general expression, you always remember this general expression. Often question comes in density of state. They will give it 4 curves. Now out of this 4 curve you have to find out the correct density function. So you will always remember the general formula. And most of the question in NetGate, the question look tough. But if you understand the question, then you can easily find out the answer. So always remember the general formula. You not so much necessary to remember all the constant. So what is density next? What is density of state is very important. But this calculation is never gives in a book. Okay. In book, I follow the book. Donald Newman, it is not given. Donald Newman, it is given, and Jacob and Milman, semiconductor also. Condensed matter physics, Descartes, Kittel I am following. But only they have discussed about 3-dimensional case, but they are not giving any expression in 2-dimensional or 1-dimensional. But in exam often asks in 2-dimensional or 1-dimensional. Okay, that is why you always remember the general formula. Now, why this density of function is so important? Suppose I am giving an example. Suppose flux equal to E dot ds. This is an electric flux. Suppose electric flux moving in all directions. I take a A4 size paper here. So what happened? Electric flux is moving from this side to this side. Suppose wind is blowing from left side to right side. So I take a A4 size paper and I want to measure how many flux coming through this A4 size paper. Then this is E into area of the user interest space. Okay. Similarly, if we multiply suppose number of electrons, if you want to multiply, then if you multiply density of state function, this is a density function, okay? Density function into average number, then you will get the total number of electrons. Okay. That means what? This density of function play the same role whatever done by surface area of that plate. Okay. Suppose another example I am giving you here. Suppose in my room, okay, there's 100 square meter. My room area is suppose 100 meters square. Okay. Suppose one share accommodate 100 room. And this room, suppose I have 100 bench I can accommodate. Suppose I have a room, there is 100 bench. Okay, each bench occupied by average 5 number of students. How many students I can accommodate? 100 into 5. So 100 play the same rule in this example, and density of function play the same rule in our calculation. That is why density of state you will find everywhere. Okay, and it is in semiconductor or condensed matter physics, it is known as the density of state. In statistics, it is known as the number of available microstate. Okay, the name is different. In quantum mechanics, number of what is a degenerate state? Basis vector. Okay, in quantum mechanics, you will see the wave function is like that, a phi 1, a phi 2, a n phi n. But this expression, if I tell you in terms of statistics, I will tell you this phi 1, phi 2, phi n, phi n, there is a n numbers of microstate available for this wave function. This one wave function means it will represent a particular system. It may represent electron or it may represent Hazarika. Okay, and it is number of microstate means in statistics 1, 2, 3 n numbers of microstate. But in quantum mechanics it is called basis vector. Okay. So density of state, that is why important. So you need why we always write expression. Have you seen this expression? Have you seen this expression? N equal to Dn. Before going to calculation electron concentration in semiconductor, I want to clear the basic why it is so important. Why we have to learn density of state. Why it is often asked in the exam. That is why it is not very important to understand. So you have seen this expression frequently. D, okay, into Fe, Fe, Fe. Have you seen this expression? Everywhere you will get it. Why Fe is product? I am giving one example. Why Fe is product? Okay, I am a simple calculation giving you so that you can understand. You have studied a black body radiation calculation, average number of photon. Average number they will calculate it n e to the power n beta e sum of e to the power n beta e. So it will give you expression. If I take this one, I can n x to the power n x to the power n. What is x? X is equal to e to the power beta e. I can express like this also, right? This part is assumed as a x. So if you find this expression, you will get finally e to the power e kt minus 1. In case of boson, this is a Bose-Einstein statistics, but I am going to consider here electron, fermion. But I am giving an example so that you can understand why this Fe is necessary. So in case of boson, chemical potential is 0, e to the power e minus mu by kt minus 1. It is what? Bose-Einstein function. Chemical potential is 0 in case of boson, okay, in case of photon. So that is why I put mu. Mu means chemical potential. It is also known as a Fermi energy at 0 degree Kelvin, equal to Fermi-Dirac distribution function. So it is means average number means F. In case of photon, photon is a boson. This is Bose-Einstein function, probability function. Okay. So, so what is the total number of photon in cavity? We have a calculator like this, right? Total number of photon in a cavity, G D F. We finally we get 8 pi V H Q H nu e to the power H nu by kt minus 1. This type of formula we are getting, right? This type of formula we are getting, right? This is the density of state. So that means any number, total number equal to density of state into average number. Okay. Similarly, if we total energy, if we find out the system density of state, you have to multiply with the average energy. Okay. Why this average energy? But in case of energy expression, in this is E, total energy in a system, we always consider G, D, F, E. Why this expression used? You see, again I am telling you another example. Average energy is calculated N is cos omega or H nu. You can put H nu also. H nu e to the power N is nu beta the e to the power N is nu. Black body radiation calculation. H cos H nu beta. If we calculate this one, H nu is constant, so it will be average number. So it is E average number. So the total energy is density of state. Always remember, density must be there. Density play the same role as total volume. Okay, it acts as a total volume into average number, total number of electrons. Always remember. So density into average energy. So average energy G D average energy means E into N. And N is what? N is the average number of particles. So it will equal to the corresponding probability distribution function. But here I am considering photon, so it will be Bose-Einstein function. If I consider electron, then it will have to replace Fermi-Dirac statistics. Okay, this average number means corresponding distribution function. That is why we always put like this. Okay, so that means any number any quantity if you want to measure, suppose in continuous system, integration means continuous system. Suppose any number, total number, if you want to measure any number, suppose x, total number x you want to measure, then z, d must be there. And if it is one dimension, then you have to replace the density of state one dimension. If it is two dimension, then you have to put two dimensional into average x. Okay, clear? That is why it is always density of state is very important. Now I consider concentration and electron concentration is Cv. How to calculate? How to calculate? This is okay. Now you have to understand before going to that, because n equal to total number of electron G D, okay, into average number. Average, this is average number. Average number means, what is average number? I have already shown you. This is for electron, so you have to replace Fermi-Dirac statistics. Fermi-Dirac statistics. What is a Fermi-Dirac statistics? If you see, equal to 1 by e to the power e minus mu kt plus 1. In case of boson, it will be minus 1. In case of fermion, it will be plus 1. Okay, remember? Now, in exam, what is a chemical potential? Sometime in exam it is asked. Chemical potential is known as a Fermi energy at 0 degree Kelvin. Always similar. So in books, that is why it is sometimes it is represented by mu, sometimes it is represented by E by EF. This is Fermi-Dirac statistics. Okay. Now we have to. I am going to do the calculation. Before that, I have to give you some basic idea about Fermi-Dirac statistics. Fermi-Dirac statistics. I want to learn what is a Fermi-Dirac statistics. E to the power E minus EF. Now I am replacing EF by KT plus 1. Okay. And this is equal to the, always remember, average number of particles. This is occupation number. This is all one probability function. Okay. This will give the number of electron occupied in particular energy level divided by total number. Have probability. This is nothing, just probability. And probability nothing, just fraction of particle occupying in a particular energy level E. Okay. Now, in case of semiconductor, I consider first T equal to 0 Kelvin. Suppose at 0 Kelvin condition, what happens? At 0 Kelvin, if I consider E is E minus EF, E is greater than EF, then what happens? E minus EF is greater than T equal to 0. E minus EF equal to how much? Is EF greater than EF? Then what happens if you put it here 0 up? 0, 0, 1. But before that you want to know. E is less than EF. This condition you have to know first. If E is less than EF, then what happens? Then e to the power, then this function, I am talking e to the power E minus EF by KT equal to how much? Equal to e to the power minus infinity divided by 0. It will be how much? E to the power minus infinity equal to how much? It is 0. It is 0. So Fermi-Dirac statistics equal to how much? It is 1. Okay. Then 1. Okay. Next, when T is greater than when E is greater than EF, then F equal to E is greater than EF means this is positive. Then this integral comes to what? E to the power infinity divided by 0 infinity, e to the power infinity plus 1. And this part will become e to the power infinity. E to the power infinity plus 1, how much? Is equal to infinity. So this whole term becomes infinity. So this term whole become infinity. 1 by infinity plus 1 equal to infinity. So Fermi-Dirac statistics equal to 0. That means what? That means what? That means this is a probability function. Probability. This probability equal to fraction of particle. This is fraction of particle occupying a particular level. Okay, this is total number of electrons. Okay, this you have to plot. That means this is EF, this is E, this is probability. What do you understand? Below the Fermi level at 0 Kelvin, below the Fermi level, all electrons are occupied. And all energy level below the Fermi level occupied by electron at T equal to 0 Kelvin. Okay. But when you increase the temperature, greater than T is greater than 0, then what happens? This probability function, if you plot this in this one, half. And what happens? Fe, E equal to EF, Fermi energy equal to 1 by e to the power 0, 0 plus 1 equal to 1 by half. That means at Fermi energy, at E equal to Fermi energy, the probability of occupancy is 50%. 50% means 50% of electron can occupy a particular energy level E. Okay, this is the meaning of the probability distribution function. Remember, probability distribution function is a fraction of particle. This is a fraction of particle occupying energy level E. Okay, this probability distribution function will tell you distribution of electrons in particular system, how it is distributed. Okay, and this is nothing, just fraction of particle is a probability. Now I will calculate concentration of electron in conduction band, G, D, and Fe. Okay, if I calculate this, so G equal to how much? G equal to I have considered it is A, E half. Okay, A means I have already given 4 pi V. V is there. V density of state. V is Q twice M. Okay, C by 2 E half. This is the expression. But here I will not put this is G equal to, I will put 4 pi V is Q twice M C by 2. I will put E minus EC half. Why E by EC I put it here? I will tell you. Into Fe. Okay. Why I will put this one? Instead of E, I will put. Have you remembered this diagram in conic penny model? Conic penny model, have you remembered this diagram? I hope you have remembered this diagram. In conic penny model, EC, K, okay, this is K. Have you remembered this diagram? This diagram means total energy E is equal to EC plus A cos square K square by twice M E square. This is conic penny model. I am not going to give you detail because of time. So conic penny model, this is a conduction band energy. It will look like this shape. That is why total energy, this part energy is EC plus this part. Okay. So if we do the calculation, I am not going to give you. This is simple calculation. B twice M C by 2 integration E minus EC half and Fe. Fe means 1 by e to the power E minus EF by KT minus plus 1. Okay, D. Okay, and now you assume that E by EF is by KT is very, very high. Then what happens? You can ignore one. It will, this Fermi statistics become as a Bose-Einstein statistics. You can calculate it. 4 pi V is Q twice M T by 2 and E minus EC half. And now I am going to consider the electron in conduction band. Conduction band start from EC to infinity. So you have to put EC to infinity. Okay. Then it will become E minus EF by KT kT d. Why I put? If E minus EF is very greater than kT, temperature energy, this is thermal energy, kT is thermal energy, then it is become the Bose-Einstein statistics. Okay. This is, you can calculate gamma function. Gamma function, have you remembered the gamma function? Have you remembered the gamma function? Gamma n plus 1 equal to 0 to infinity e to the power minus x to the power n dx. Okay. And gamma n plus 1 equal to n factorial equal to n gamma n, and gamma half equal to root pi. This is related to gamma function. Use this integration. E by EF by kT equal to, consider x. Okay. And then you will transform this equation. You will get a function descent. Then after that you put the value. Then using gamma function. Okay. So it will take time. That's why I am not going to give you. Otherwise I can give you. I have I have given you the how gamma this type of problem is solved is using gamma function in statistical lecture. If you want to understand the use of gamma function, then you can see that video. Okay. So due to time I am going fast. So concentration of electron, I will, if we solve using gamma function, I will get 2 into twice pi me star kT divided by a square t by 2 e minus. Now how to remember? Now I am considering the electron in conduction band. Electron conduction band start from this part, EC to R. Okay. So this way remember, e to the power EC minus E over kT. Okay, this is the expression. Similarly, if I calculate same procedure, if we calculate hole in valence band, then expression will be like this. I am not going to give you because of time. Integration G E D and 1 minus Fe. This is I am going to whole. That's why I put this is a whole for Fermi dx statistics for whole 1 minus Fe. Fe means it will measure the electron concentration. 1 minus whole, it will measure the whole concentration. After that it will be same calculation, 4 pi V H cube twice m H 3 by 2 E minus EV half e to the power minus E minus EF by kT d. If you do the calculation in the same procedure, you will get the whole 2 into twice pi m A star kT divided by a square 3 by 2 e to the power EV E minus EV. Okay. So how to remember? First below, then EV. This is what you see the diagram. That this is how you have to remember. This is EV, this is EC, then EE. So here you will get E, then EV. Okay, this way you have to remember. This is only to remember. E minus EV, then EV pisot EC, then E. Go upside. Okay. Now you have seen that I am writing here ME star and ME star. Why? This is effective mass of electron, not free mass. What is effective mass? Suppose, why it is called effective mass? Suppose one electron is free in your hand. Suppose one electron in space. This electron is moving. Practically, ideal electron never get. Isolated electron you never get. But hypothetically I consider there is a one electron in free space moving freely. Okay. Another electron will inside the crystal. So inside the crystal, when you talk about the electron inside the crystal, this electron, there will be multiple number of electrons. So there will be electric field. This other electron inside the crystal will affect the motion of electron and create the electric field. It will influence the electron inside the crystal by other electron. So accordingly, mass will affect it. So that is why effective mass is used. Mass which is free electron mass, isolated electron, is never be equal to the mass in free electron. mass in so mass of electron inside the crystal. So this is mass of electron inside the crystal. That's why we use effective mass. You have already studied in condensed matter physics, conic penny model, and you have, I think you have effective mass of electron. You have find this formula. This effective mass of electron is depend on the energy expression and wave vector. Have you? I think you have already studied. This is the expression of effective mass in condensed matter physics. So there is a long calculation. All say this type of calculation often asked in exam. So that is why I am not going to give you that part. But you remember, this is effective mass, mass of electron inside the crystal, which is not equal to the mass of isolated electron. That's why I use this one. Okay. So this is the expression. How to remember? This is a constant. This is, and this constant is known as a 2 into NC. NC effective concentration, effective density of state. E to the power EC minus EF KT equal to NV e to the power E minus EV by KT. This is the expression. And NC NV electron concentration. Density of state means number of electron. Why? Because this is a numerical number. Always remember. This is a concentration of electron where V is absent, V is there. This is number of electron per unit volume. This is number of electron per unit volume. So this exponential, this will numerical value, this is also number. So it will have centimeter inverse. This is number of electron per centimeter. Okay. So this expression I remove it. Now I have to calculate the law mass action. These things you have to know. These things you have to know because these things tell a lot of things about the semiconductor. How law mass tell that N equal to P equal to Ni square. I am considering intrinsic semiconductor. Number of electron equal to number of hole. So this is a law mass action. I can replace Ni square, N square equal to N into P. So if I product N into P means 2 into first electron twice pi me star kt a square 3 by 2 into 2, it will be 4. 2 pi me star kt a square kt 3 by 2, and exponential it will product will be there. First one is EC minus EF E, okay, plus E minus plus EV by K. Is it okay? Now if I take 4 into this, forget about 4, I take only a constant. All the term except temperature, all the term I will put inside the constant. So constant it will give T Q. Okay, this will give, this will cancel. EV minus EF is how much? Minus EV minus EF EC by KT equal to AT cube e to the power minus del E. Why del E? By KT. So del E, EC minus EV is a band gap. Okay, that's why I replace del E, or you can replace another gap EG also. No problem. EG also. What we can understand, this is a law mass action. Law mass action tell that N square equal to AT cube e to the power minus EG band gap by KT. Okay. This is equal to what? AT cube 1 plus EG by KT plus half EG by KT. Is it okay? Is it goes like that? Now you think this is exponential expression. Now you think when temperature of semiconductor is increases beyond 0, okay? When temperature of semiconductor, that's what I am telling you starting part. When you increase the temperature of semiconductor, number of carrier in conduction band is gradually increases. As a result, current in semiconductor increases. That's why it is called negative coefficient of resistance. Now you see in terms of equation. When you increase the temperature, when T is very high, this term tends to 0, this term obviously tends to 0, this term obviously tends to 0. So this expression n square equal to 8e cube. Approximately this expression will come. What does it mean? See, when we increase the temperature, this below this denominator part, this term will tends to 0, this term tends to 0, this is denominator become 1, clear? So when you increase the temperature, this T, this is power Q, increase the temperature, then carrier concentration of electron is gradually increases. That means what? Resistivity decreases. That is why it is called negative coefficient of resistance. And this law is same law related to Kepler's third law. Is it analogy to Kepler's third law? What is a Kepler's third law? Tell time period of revolution of planet is proportional to the semi-major axis, cubic of semi-major axis. Is it Kepler's law? Similarly here, but here it is not. This is analogy. If you want to remember, you compare this equation with Kepler's law. Okay, this is Kepler's third law. Kepler's third law tell the square time period of the revolution of the plane around the sun equal proportional to the cubic of semi-major axis. Similarly here, square of coefficient of electron concentration equal to proportional to power of temperature. If we increase temperature, then number of constant gradually increases. That is why it is called negative coefficient of resistance. This expression always remember. Okay. And the last one I want to tell you, Fermi level. Fermi level. So in intrinsic semiconductor n equal to P, correct? So if I replace n equal to how much? 2 into twice pi m e star kt a square e to the power minus ec minus e by kt equal to 2 into twice pi m e star kt divided by a square e to the power e minus ep by kt. Okay. So forget about constant, this constant. So if I write m e star by m e star to the power 3 by 2, sorry, 3 by 2 is there, 3 by 2 is there. 3 by 2, is it okay? Divide this part, equal to e to the power e minus ep plus e. This is I am going to calculate the Fermi energy. That's why I put EC minus EF, EF minus EC, and EV, EF plus EF, EC, EF, EF, then EF, then plus EV. By kt. Is it okay? Then I will take the log. Log ln. Ln means it will be 3 by 2 m e star m e star. Okay. This will happen what? Log lolo it will go e plus ev minus twice ef Fermi energy. So initially it is E, but I am going to calculate Fermi energy. That's why I put EF minus ET. So it will be this. Okay. So finally, what I am getting, EF equal to, if you solve this equation, EF equal to KT will be there. Then it will be EC plus EV by 2 plus 3 by 4 ln me star by me star. Okay. What we understand? The Fermi energy, now you don't tell that. The Fermi energy is always fall in the middle of band gap. Okay. Why? These equations tell. I am not telling. These equations tell that Fermi energy. Oh, sorry. One term is missing. 3 by 4 KT is there. Okay. KT will be there. ln me star. Okay. This equation tells that Fermi energy fall in the middle of band gap only when temperature is 0. T is 0 means this term will be 0. Then it will be half of middle of band gap. That means this is EC, this is EV, then Fermi energy fall in the middle of band gap. Average means half. And one condition, at temperature T equal to 0, Fermi energy fall in the middle of band gap. Another condition, when effective mass of electron equal to effective mass of hole, then it will be ln1 is 0. So then Fermi energy fall in the middle of band gap. Otherwise, if M star is greater than M star, then this is a Fermi energy. This Fermi energy slightly move toward the conduction band. Okay. If M less than MS or MS is greater than ME, then what happens? This will be negative. So Fermi energy fall toward slightly below the original line. Okay, toward the conduction band. Clear? Okay. I think you hope understand why it is called negative. So important thing is that why it is called negative coefficient of radiation. Fermi energy this expression. And a question often comes this expression and negative coefficient of radiation. You have to plot. The last time in GATE exam, they ask you which of the following figure is correct. N and T. So N square and T. N square N proportional to T square. T cube. This is what. So if I put this one T and you can draw this diagram, the curve you can easily find out. Okay. That's what they are going to ask you. So next time, in the next class, I will tell you that one transport phenomenon of semiconductor, current density, and Hall effect. Hall effect is the most important things for exam purpose. What is Hall? Okay. Thank you.